Hello and welcome to AP Pre-Calculus. Today's lesson is 1.5, Polynomial Functions and Complex Zeros. All right, a little quick review of Algebra 2. If I would ask you to find the zeros of function p, you would have to factor it, and you would get x plus 3 and x plus 4. Those are called the factors of the polynomial, but the zeros would be taking each of those parentheses and setting them equal to 0, which would give us these. And going the other direction, if I were to give you the zeros and ask you for the polynomial function, you could put these back into their factored form. That would be x plus 5. This one's a little bit more challenging because if you can't put a fraction back into a factor, so we'd put the 3 in front of the x, change the sign of the 2, and then we would just FOIL that out. We're not going to waste time with that because that's all Algebra 2. So let's keep going. All right, sometimes you have a repeated 0, and if we have that, we call it a multiplicity. And you'll usually see it, the factor will have an exponent with it, all right? So typically, we know that the graph of a polynomial passes through the zeros of the graph, all right? Notice I said typically. However, when a 0 has a multiplicity greater than 1, the graph behaves a little differently there. It does some weird things, okay? So look at our graph over here on the bottom right here. So I'm giving you the function to the left. It's some weird looking function. Notice that they both are going in the same direction. That means the degree had to be even. So how can I look at my function and know that the degree is even? So each one of these things that has an x is called a factor. That negative 0.01 is not a factor. That is a coefficient. But the x plus 4, x plus 1, and x minus 3, those are factors. If you take all of the exponents with those factors, the degree of each factor, and add them together, that would give you the degree of the function. So there is a 1 here, and if I add the 1, the 3, and the 2, I get a 6. That 6 is the degree of the polynomial. Notice each factor had a degree, but if I were to FOIL this all out, that would be a polynomial, and its degree would be 6, which means these have to go in the same direction, and because there's a negative here, that's why they're both going down. So I have 3 different factors with different zeros, right? And each one of them act a little bit different. Like this is our normal looking 0. We're used to something that just kind of goes straight through, almost looks like a line going through there. Not quite a line because this is not linear, but that is a linear factor. So that's why it does kind of look like a line going through negative 4. But look at negative 1. Remember, we'd set this equal to 0, get negative 1. I have a degree of 3, so it does something weird. That doesn't look linear there. Like it has curves and stuff, right? But it still goes through the x-axis. But look at what happens at our 0 of 3. I'm coming up and I get to 3 and I bounce off. I don't go through, right? So that's if it has an odd degree, if that factor has an odd degree, it will go through the x-axis. But if it has an even degree, it's going to bounce. All right, here we go in example 1. We start out with a. We have a function, f of x. We want to know the degree, okay? So we are going to take all of the exponents. See, everything is factored. That's kind of important. Everything right now is factored as far as we can factor it. And I have multiple x's. So I'm going to look at the degree with each of those factors, and I'm going to add them all up, and that should equal the degree of our polynomial function. So I got a 3, a 1, and a 2. That gives me a 6. All right? The zeros, I want to know what the actual zeros are, not where they're at. I want to know what they are. So you're going to give them to me in ordered pair. So when there's an x on the outside, I set that equal to 0, and I end up getting 0, 0. When I set x plus 1 equal to 0, I get negative 1 comma 0. and then I get 4 comma 0. And if you go back and look at the exponents on each of those, this one had a multiplicity of 3. This one had a multiplicity of just 1. And then a multiplicity of 2. Okay, here in B, they were a little bit mean to us because they left one that wasn't factored. So that's what I would do first. I would factor that. Try and factor it correctly would be nice too, but you know, whatever. All right? And if you notice, those two guys are the same, so I could rewrite this as 3x minus 2 to the 5th x plus 2. Because remember, if we're multiplying like bases, we add the exponents, all right? So my degree, again, is 6. My zeros are 2 comma 0 and negative 2 comma 0. Multiplicity, well, this one had 5. This one had 1. Okay? I want you to look at those multiplicities. Add up those numbers. What do you notice about those numbers? They equal the degree, right? So let's move on to this last one here. I'm going to move this over so we can see. Well, they were mean to us again, so we have to do some factoring. So let's start out GCF, because we always GCF first. Do not forget that. Oops, not plus 7, minus 7x plus 12. All right, so we got x minus 3, x plus 2, x minus 3, x minus 4. Let's rewrite that because I have two x minus 3's. Let's go ahead and put squared. All right, there we go. The degree. I have 4 x's, so each of those are going to count. So I have a 1 there, a 2, a 1, and a 1. So let's add those up. I get a 5 this time. And my zeros, well, whenever there's an x on the outside, it's 0, 0. And I got 3 comma 0, negative 2 comma 0, and 4 comma 0. Multiplicities. I'm going to write multiplicity once. So we got a 1, a 2, a 1, and a 1. If I add all those up, they make 5. So there you go. There, I scrunched it back down so you can see them all at a glance. Okay, so now we're talking about complex roots. Remember, zeros are when we cross the x-axis. And if I cross the x-axis in 2 different places, between those places I have to have a relative max or a relative min. Okay? Well, let's look at this graph over here. That is definitely a relative min, but I didn't cross the x-axis, which means I don't have any zeros, but I have to have something going on because I have a relative minimum. So what's going on here? Well, that's when this complex root comes in. If you remember from last year, the imaginary numbers, I know we all loved them, they didn't go away. So that's what we're going to talk about now. Some polynomials have roots that can contain imaginary numbers. This means you will not see them crossing the x-axis. So we will not see them on the graph. The graph we have over here is the function x squared plus 1. And we can actually solve for that, seeing as how last year we opened up a brand new pool of numbers so we could solve a problem like this. And when we take the square root of negative 1, if you remember, we get an I. And don't forget, if we take a square root, we have to put plus or minus, because that 2 tells us I should have 2 answers. That is the fundamental theorem of algebra, okay? So all imaginary roots come in pairs because of that plus or minus, okay? So if I give you a plus bi is a root, then I know for sure that a minus bi has got to come along. When we take a number out of the imaginary pool of numbers, I cannot take one out without its partner. They come in pairs, and we call those pairs conjugate pairs. All right, so look at example 2. Real easy. What are the conjugates? If I took 4i out of the pool, negative 4i comes along. If I take negative I out of the pool, I comes along. 2 minus 3i has its partner 2 plus 3i. Negative 4 plus 2i, now here's a tricky one. I don't change that -4, but I do change that plus to a minus. So -4 plus 2i, -4 minus 2i comes with it. Well, look at that. A little foreshadowing on the last page. So we have the fundamental theorem of algebra right there. A polynomial with degree n has exactly n complex zeros when counting multiplicities. Okay? So that doesn't mean that all of your answers will have an I in them, because if you remember, a complex number is a plus bi. If it crosses the x-axis, like let's say it crosses it at 5, I could write 5 plus 0i. So a rational number is a complex number also. It's just it doesn't have the imaginary partner because it was a 0. Okay? So here we go. On example 3, the graph of the polynomial function is shown in the figure. It's known that I square roots of 3 is a 0. If f has a degree of n, what is the least possible value of n? So if I have I square roots of 3, then I know that I have negative I square roots of 3. So those are two zeros right there that we can't see. They don't cross the x-axis. So let's look at the x-axis. This one goes through, so I know that x minus 3 had to be one of the factors. And then this one bounces, so I know that x plus 1 had to have an even exponent. This has to be an odd exponent. And this one says least. So what's the least odd number that I can put there? Well, that probably shouldn't have used an O because that looks like a 0. That could be a 1. What's the least even number I can use? That would be a 2. So let's count up all of our numbers here. We have 1, 2, 3, 4, 5. So 5th degree polynomial is the least it could be. This right here, I don't know. It's without more information. I don't know if that's x to the 3rd, like x minus 3 to the 3rd, to the 5th, to the 7th. I just know that it's odd. Same with over here. I don't know if that's an x plus 1 squared, an x plus 1 to the 4th. So that's why it's saying the least possible value. There's an infinite number of possible outcomes for the degree, but the least possible is 5. All right, you're going to hear me say this a lot this year. Words are important, okay? So let's look at this reminder over here to make sure that we remember some of the things that are going on. When we write f of x, we are referring to the y value of the graph. So if f of x is greater than 0, then we know that the graph is above the x-axis. If I say f of x is less than 0, I know that the graph is below the x-axis. Okay, let's go ahead and look at example 4 here. It says, where does f of x equal 0? Where is the y 0? That means, where do I touch the x-axis, right? So we touch the x-axis at -3, at -1, and at 3. Okay? B is asking, where is that function positive? Meaning greater than 0, by the way. Well, positive is above the x-axis. And I got a couple of areas that are above the x-axis. I got this guy here and this guy here. So I got 2 sections. And we want to give that in interval notation. So I know from -3 to -1, and I use parentheses because I don't want to include those, because at -3 I was at 0. I'm not positive. All right? And then I'm going to union that with 3 to positive infinity. Okay? Now, I don't know if you have to put that, but it's a good habit to get into. Okay? So let's look where we're negative, because that's what C is saying. Where are we negative? And that would be down here. And I don't know why we have the or equal to, so we'll worry about that in a little bit. All right, so we got negative infinity to 3. And I'm going to go ahead and always put that. I'm going to go ahead and put the bracket. I do think that they don't really care all that much, but because I teach Algebra 2, the or equal to means bracket. So, and then we're going to union that with -1 to 3. And those get brackets on both because they both touch 0. Okay. So moving on, we're solving nonlinear inequalities. And so in this box is something that we have never done in Algebra 2. So definitely want to pay attention to this. So what we're going to do is we're going to solve for f of x, factoring. We've got to factor and all that good stuff. We're going to create a sign chart. Okay, we'll have to practice what that means. Then we're going to test a value in between each of those intervals to see if the intervals are either positive or negative. And then we're going to interpret the sign chart to answer the question, okay? So here we go. We have solved, in example 5, we have already solved the inequality, and we want to make a sign chart. So really what you want to do is you want to make your x-axis, like we're back in pre-algebra, and this is going to give me x equals 3, x equals -1, and x equals -4. This is a number line, all right? So put -4 where it's supposed to go. Put these all, not like your spacing doesn't matter, okay? But now we're going to put some dots here like this, right? And what I've done is I've just cut this x-axis into 1, 2, 3, 4 sections, right? And what I want to do is I want to find out what are all of these values out here? Are they positive values or negative values? They'll all be the same. Same here on each of these. So how am I going to do that? I'm going to pick a number out here. Let's say I picked -10, all right? I don't really need the answer, although you could do it if you want to. But if I put a -10 into the first x, right here, I'm putting -10 in all of these, ask yourself what kind of sign are you going to get out? Well, -10 and -3 make negative. -10 and +1 make negative. -10 and 4 make negative. And if I multiply all those together, I'm going to get a negative. And then I do it again with a number in between here. What's a number in between there? I don't know, -2. Let's try -2 out, right? So if I put a -2 in here, I get negative, negative, positive. Well, that's going to make a positive. And then I do it with a number in between here. I like 0, but it doesn't really matter. If I put a 0 in for each one of these guys, we're going to get negative, positive, positive, which gives me a negative. And last but not least, if I put it in there, I'm going to get positive, 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 and that gives me a positive. So now the question is asking, where is this function greater than 0? Well, what kind of numbers are greater than 0? Well, positives are. And I'm positive from -4 to -1, and I'm positive from 3 to infinity. All right, let's go ahead and give example 6 a try. Everything's factored out, right? So I have -2 and +5. Only these two this time. There we go. Let's go ahead and put some dotted lines there. So there's my chart. Now I only have 3 things to test here. So I'm going to go ahead and test -10. I love -10. Why not? So if I put a -10 in here to the first one, I'm going to get -8, but I'm going to square it, so that's going to be positive. And then I'm going to get negative with a negative. -10 minus 5 is still negative. So this is negative. All right? I'm going to put 0 in because I love putting 0 in. So if I put a 0 into the first one, I get 2 squared. I'm going to get positive. Then I get negative. Then I'm going to put +10 in for the last one. And I'm going to get positive, positive, and it looks like this. Now I'm looking for where is it less than or equal to 0? Well, that's going to be at negatives, right? So -2 to 5 is where my function will be less than or equal to 0. And notice I use the brackets. Again, this is the type of question that I would probably think would be on the multiple choice, and they wouldn't have parentheses -2, 5 and brackets -2, 5. But just so you know, that's how it should be written. All right, you might not have touched on this idea last year in Algebra 2. It was there. We spent very little time on it, but it does come up in pre-calc, so let's go ahead and look at it. I do want you to notice that our x values have the same jump every time, and that's important, okay? Otherwise, we'd be in a little bit of trouble doing this one. So what we want to do is we want to find the differences, okay? So I'm going to do -3 minus -2. I'm going to do -1 minus -3. I'm going to do 4 minus 1. I'm going to do 12 minus 4. If those were all the same, it'd be a linear. It'd be a degree of 1. I only had to subtract one time. It's going to be linear, but they're not. So now I'm going to do 2 minus -1, 5 minus 2, 8 minus 5. My second difference is the same. So this would be a quadratic, right? This would be x squared because it took me 2 to get there. Let's try it with b. 0 minus -2 is 2. 10 minus 0 is 10. 27 minus 10 is 17. 50 minus 27 is 23. That's not even close. Let's try it again. 2 minus 10, 8. 7. 6. That didn't work either. Let's try one more time. -1. -1. So first, nope. Second, nope. Third, yup. This is a cubic. This is an x to the third problem. All right, now we're going to talk about even and odd functions. Different than even and odd degree. Even and odd degree talk about end behavior. Even and odd function, something very different, okay? So there's a couple things going on here. Obviously, even is different than odd. So I'm going to pick some points on the left-hand side of my first graph, some easy points. So let's see. This one is, what is that? -1, -1. This one is -2, -3. And this guy up here is -3, 2. All right? So an even function is saying this right here. To be even, it's saying, hey, let's change the input to the opposite sign. We're just going to change the sign of x. If I get the same y value out that I got when I put the other sign in there for x, then this would be an even function. So what does that mean? Let's look at our first one. So this guy right here is the x value. He's a -1. So if I want to change the value of him, it'd be +1. But the y value didn't change. So it'd be 1, -1. Well, look what I got. I'm on the graph. The second one, -2, would change to 2, but the y would not change. I'm right there. I'm on the graph. And my last one, the -3 would change, the y would not change, and there I am on the graph. All of those points lined up. It is symmetric across the y-axis. That's what makes it an even function. Moving on to the odd function, boy, a lot of things are going on here. I have to change the value of my x function, and when I do that, my y value changes signs too. So let's pick a couple points right here. All right, we'll pick this guy right here. I don't know. We're gonna basically call him -1.9, 2. Let's pick this guy here. He's -3, 0. Is there anything else that's an easy one? Let's take this one right here. What is that? Like -3.5, oops, that's not a comma. -3. Let's give those a shot, okay? So let's come down here. Let's take our first one. I'm going to change the value of my x to +1.9, and it's got to change the value of my y too. Both of those things have to change. Well, let's go over to +1.9 and down. Hey, I'm on the graph, right? I'm going to change the value of my 3. I'm going to change the value, well, changing the value of 0 makes it stay 0. Hey, I'm still on the graph. The -3.5 becomes 3.5. Got to change the value of y too. There we go. Let's go over 3.5, up. Hey, we're on the graph. That's how I think that's probably the easiest way to think about even and odd functions. Just to let you know, an odd function is symmetric around the origin, which means it's symmetric to both the x and the y axis. It's the line y equals x, basically. Okay? So if you do a double flip, I guess if you want to think of it that way. But I think the easiest way is to do it with the points. All right, example 8. We want to determine whether these functions are even, odd, or neither. So what we're going to do, to check for even, remember we take the x's and we make them negative. So I'm going to do negative x, the fourth goes on the outside, minus negative x, the squared goes on the outside, plus 5. Well, if I do negative x times itself 4 times, I'm going to get positive x to the fourth. And I'm going to minus negative x squared. When I multiply negative x times itself twice, I'm going to get positive x, so I'm going to minus a positive x squared plus 5. When I changed the values to negatives, this guy stayed the same. This is an even function. And you can't be even and odd, so there's no point in checking the odd. P.S. There's even exponents, so there's no way it's going to be odd. Same way with if you have odd exponents, there's no way it's going to be even. So on this one, I want to see if I put negative x here, would I get a negative of this? Which means, would it come out negative x cubed minus 3x plus 1? So let's do it. So here we go. Negative x. I'm going to put negative x in there with a cubed. Negative x there, minus 1. When you multiply negative x times itself 3 times, you get negative x cubed. That part's good. 3 times negative x is negative 3x. That part's good. But I get minus 1 here at the bottom. I need it to be plus 1. This is minus 1. It is not odd, so it must be neither. Let's talk about how maybe we can do a little bit less work on some of these sometimes. I'm going to tell you right now, if I'm checking to see if something is odd, I can't really have any exponents that are even, and that should make some kind of sense, right? So if you look at the exponents in B, I have an odd exponent and an odd exponent, but at the very end, you may think it's an odd exponent, but I'm talking about the exponents with the x. I could rewrite this guy as 1x to the 0 power. That is the same thing. We're going all the way down to x to the 0. We just don't usually put it because x to the 0 is 1. 0 is an even exponent. So I cannot have a constant and think that I'm going to have an odd function. It just will not work. Okay? All right, let's look at C. We're trying to see if it's even, odd, or neither. I'm going to tell you right now that my end behavior, I have my limits going in opposite directions. This is an odd degree, so it can't be even. So I'm not even going to try the even. But remember, for odd, I want to put negative x needs to go with negative y, because I'm going to do this. F of negative x, I'm changing the sign of my x, and it needs to be this, and that's my y. So these two things mean the same thing. So let's check. We're just going to call this up here, we'll call it negative 1, 3. Changing the x and the y, I need to get 1, 3. I have it, right? Let's try this guy right here. That is negative 2, 0. To change the x and the y, I need to have positive 2, 0. I have it. And you can check this. So this is an odd function. There we go, right? So let's check D out. My end behavior, they're both going in the same direction. It has to be an even degree. I'm not even going to check odd because it can't work. For even, remember, it's f of negative x equals f of x, which means when I change my x, the y has to stay the same. Okay? So let's pick a couple points here. We got a point here. I got, what is that? -1, comma 1. So when I change my point, my x has to be +1. The y has to stay the same. I'm not on the graph. So it is not even. It must be neither.